Hi, welcome to Thermochemistry 2. My name is Dr. English. Today we're going to be talking about free energy under non-standard conditions. Specifically, we're going to look at Essential Knowledge 6.D.1, which states, when the difference in Gibbs free energy between reactants and products, delta G at standard state, is much larger than the thermal energy, RT, and the equilibrium constant is either very small, so then our delta G at standard state is quite large, or very large, so our delta G at standard state is going to be less than 0. When delta G at standard state is comparable to the thermal energy RT, the equilibrium constant is near 1. So that's what we're going to be focusing on today. Specifically, we're going to look at calculating delta G under non-standard conditions, free energy and equilibrium, the dependence of free energy on non-standard pressure situations, and finally some practice calculations at the end. Calculating delta G under non-standard conditions. Most chemical reactions occur under non-standard conditions. Go figure. When the concentrations, molarities, of reactants and products are non-standard, Q, which we know is the reaction quotient, must be calculated in order to determine the value of delta G. For any chemical process, the general relationship between standard free energy change, delta G at the standard state, and the free energy change under any other conditions, delta G, is given by the expression delta G equals delta G at standard state plus R, our temperature in Kelvin, natural log of Q, where Q is the reaction quotient, R is the gas constant. In this case, we're going to use 8.3145 joules per Kelvin mole. Delta G at standard state is the free energy change for the reaction with all reactants and products at a pressure of 1 atmosphere, and delta G is the free energy change for the reaction for the specified pressures of reactants and products. So that is defining all the variables in the equation, which we will be using quite a bit. Free energy and equilibrium. Thermodynamic view of equilibrium. The equilibrium point occurs at the lowest value of free energy available to the reaction system. At equilibrium, delta G is going to equal 0 and Q is going to equal K. So we can use the formula delta G at standard state is equal to the negative RT ln of K. So delta G at standard state where it equals 0, we know that K is going to equal 1, and that is at equilibrium. When delta G at standard state is less than 0, in other words, a negative number, our K is going to be greater than 1, and that is going to favor products. That's going to be favoring products. When our delta G at standard state is greater than 0 and it has a positive value, our K is going to be less than 1, which means it's going to favor reactants. And we can calculate all of this, which we are about to do. The dependence of free energy on non-standard pressure situations. So we have enthalpy, and we know that enthalpy is represented by H, and enthalpy is not pressure dependent. Entropy, on the other hand, which is represented by S, does depend on volume, so it also depends on pressure. So for our first situation, we're going to look at delta G at standard state plus RT ln of Q with a little p meaning pressure, where delta G at standard state is the free energy of the gas at a pressure of 1 atmosphere. Delta G is the free energy of the gas at a pressure of P atmospheres, so in other words, not at standard state. R is our universal gas constant, and T is our Kelvin temperature. Calculate delta G at 298 K for the reaction of nitrogen and hydrogen to form ammonia if the reaction mixture consists of 0.5 atmospheres N2, 0.75 atmospheres H2, and 2 atmospheres of ammonia. So the first thing that we're going to do is to write the equilibrium equation, where we have N2 plus 3H2 2 double arrow 2NH3 because I'm that good that I can write it and balance it at the same time. After we write the equilibrium equation, we're going to solve for the reaction quotient for non-standard pressures, where Q, if you remember, is our reaction quotient. So when we represent this, we're going to do the pressure of the ammonia, NH3, squared, because we have a coefficient of 2. And on the bottom, we're going to have the pressure of our nitrogen gas. And then finally, the pressure of our hydrogen gas, cubed. So I have set up my expression here, and now what I'm going to do is substitute in numbers. Now remember, one key thing that you should recall is that since we are working with pressures, we have parentheses around our pressures here. We do not have brackets. Brackets indicate concentration, and we are dealing with pressure. So if you're wondering about that, that's why I'm using parentheses. So for the pressure of ammonia, we're going to have 2 atmospheres on top, and we're going to ultimately square that. For the pressure of nitrogen, we're going to have 0.5. And then finally, for the pressure of hydrogen, we're going to have 0.75 cubed. And if we work this all out, we get 18.96 for our Q. And we're going to use that ultimately later on in our equation. So we're going to just put that aside for right now. Now we're going to calculate delta G for this reaction based on standard values of delta H at standard state and delta S at standard state. All of a sudden, we get delta H values at standard state for nitrogen, hydrogen, and ammonia, and also delta S values. Isn't that amazing? I'm shocked. Look, there they are for us to use. So to calculate delta H, we're going to go back to Hess's law. And remember, when we do Hess's law, we do products minus reactants. So I'm going to write out my equation that I'm going to use for Hess's law really quick. So I know based upon looking back at my equilibrium equation, we're going to have 2 moles of ammonia minus 1 mole of nitrogen gas plus 3 moles of hydrogen gas. And now I'm going to calculate my delta H at standard state by plugging these values in. So looking at my work, I know that I am starting out with 2 moles of ammonia, which has a delta H value of negative 45.9, minus 1 mole of my nitrogen, but we know that the values for the nitrogen and hydrogen, because they are elements, are going to be 0. So therefore, my calculated value for delta H at the standard state is going to be negative 91.8 kilojoules, because all of these are represented in kilojoules. Now what I'm going to do is calculate my delta S at standard state. So here's my work for calculating delta S at standard state. Again, I'm starting out with 2 moles of my ammonia. So the delta S value at standard state for ammonia is 192.8. And I'm going to subtract that from the standard state of nitrogen, which is 191.6. and hydrogen, which is 130.7. So when I calculate my delta S at standard 8, I get negative 198 joules per Kelvin. And the thing that I have to remember here is that ultimately I need this in kilojoules. So I'm going to take a moment and say negative 198.1. Oh, forgot the 0.1 there. Oh, well, you see it now. Negative 198.1 joules per Kelvin times, we know that 1 kilojoule is equal to 1,000 joules. So when we work this out, it's going to be negative 0.1981 kilojoules per Kelvin. And we're going to need that value again ultimately when we bring this all back to calculating delta G under non-standard conditions. So I've cleared out this screen because we've already written out our delta H at standard conditions and our delta S at standard conditions, but really what we need to do here next is calculate our delta G at standard conditions so we can go ahead and plug it all into delta G under non-standard conditions. So what we're going to find now is delta G under standard conditions based on the values that we just did. So we're going to say delta H under standard conditions minus T delta S under standard conditions. And we're going to take those values that we just calculated. So we know that our delta H under standard conditions is negative 91.8 kilojoules per mole minus the temperature that they gave us here, which we know is 298 Kelvin. And then we're going to multiply that times negative 0.198 kilojoules per mole Kelvin. And when this all is calculated out, we get negative 32.8 kilojoules per mole, which is what we need to move on to the final step of calculating delta G under non-standard conditions. Okay, so now what do we have? We have our delta G under standard conditions. We have an R, which is our gas constant. We have our temperature, and then we also calculated our reaction quotient. So now we have everything that we need to finally calculate delta G. So remember, R involves joules per mole, and the unit for delta G is in kilojoules per mole, so adjustments need to be made. And one thing to point out here that we really should think about when we're talking about this delta G equation is that the delta G under standard conditions does just that. It represents free energy under standard conditions. The RT ln of Q takes into account the non-standard influences, and that's how these two are coming together to calculate this delta G. So we know that our R is going to equal 8.314 joules per mole Kelvin. What we need to do, 8.314 joules per 1 mole and 1 Kelvin, is to convert this over into kilojoules. So multiplication sign and a line. We know that 1 kilojoule is equal to 1,000 joules. And then joules cancel joules. So when we work this all out, our R is going to equal 0.008314 kilojoules per mole Kelvin. Finally, after all of that work, we can solve for delta G. So delta G is equal to delta G under standard conditions plus RT ln of Q. Our delta G under standard conditions is negative 32.8 kilojoules per mole. It's a really terrible K. Plus the R that we just calculated, so 0.008314 kilojoules mole Kelvin. Our temperature, which is 298 K. And then finally, our ln of Q, and our Q was 18.96. So if I was to break down my calculations here, I'd say negative 32.8 kilojoules, that's a better K, per mole, plus, I'm going to take the natural log of my 18.96 and then multiply that against my R and my T, and I'd get 7.29 kilojoules per mole when all my units cancel. And finally, my delta G under non-standard conditions is equal to negative 25.51 kilojoules per mole. And I guess if I was being really good and I look back at significant figures, the better answer would be negative 26 kilojoules per mole, considering that all my numbers at the very beginning are to two significant figures. So yeah, need to do it to two significant figures. Phew! Let's go look at another example. Consider the reaction H2 plus F2 yields 2HF. Using data from the appendix of your textbook, calculate delta G at standard state at 298 K. Hey, look at that! Our delta G values just magically appeared. Let's look at the chemical equation that they just gave us and calculate our delta G. So we know that in order to calculate delta G at standard state, we're going to take our products, so 2 moles of HF, minus our reactants, 1 mole of H2 plus 1 mole of F2. And we're going to substitute in our numbers. So 2 times the delta G that's given to us, so negative 275.4. That was the value given in our textbook, and we used the TRO textbook. So that's kilojoules per mole minus 1 times the delta G of hydrogen at standard state, which is 0. And guess what? That's going to be the exact same thing for the fluorine. So really, it's just 2 times negative 275.4. So if we work this out for delta G at standard state, it is negative 550.8 kilojoules per mole. So that's a way to calculate delta G at standard state when the values are given to you. So that's nice that we have that delta G at standard state, but what if we suddenly change some things? So we're going to come back to this delta G at standard state, so make sure you've got it written down. Now we're going to calculate delta G under non-standard conditions at 298 K if the reaction mixture consists of 0.8 atmospheres of hydrogen, 4.5 atmospheres of F2, and 0.36 atmospheres of HF. The first thing that we're going to need to do here, because we're under non-standard conditions, is calculate a Q. Calculate our reaction quotient. So I'm going to write an expression to represent this. We are dealing with pressures, so I'm going to use parentheses. HF squared will be on top of my reaction quotient. H2 on the bottom, F2 on the bottom, and then I'm going to plug in my pressures. So 0.36 squared. My H2 is going to be 8 atmospheres, so 8.0. And then my fluorine is going to be 4.5 atmospheres. When I calculate this out, I get 0.0036, which I'll ultimately use to represent Q. So delta G is equal to delta G at standard state plus RT ln of Q. We'll take the previous calculation that we did to find delta G at standard state, which was negative 550.8 kilojoules per mole, plus our R, which we calculated way back in our previous question, so we're not going to do that again. So 0.008314 kilojoules, because remember, under normal circumstances, it's in joules. Kilojoules per mole Kelvin, 298 K, and our ln of the Q that we just calculated, which is 0.0036. And if I work all this out, my delta G here would be negative 564.7 kilojoules per mole. And when we have a negative delta G like we do here, that means that we are going to have a spontaneous reaction and we're going to favor products. So what did you learn? We talked about calculating delta G under non-standard conditions. We looked at free energy and equilibrium, the dependence of free energy on non-standard pressure situations, and then we did some practice calculations at the end. Need more help? Feel free to contact me. Have a great day.